Okay, welcome everyone. Thanks for joining us on this webinar today. As I mentioned, we'll be taking questions after this presentation. And so if you have any questions, please place those into the chat bar on the left, and we'll get to those after going through the presentation. So the purpose of this presentation is to summarize findings from a recent report that was jointly authored by researchers from Lawrence Berkeley National Laboratory, Argonne National Laboratory, and the National Renewable Energy Laboratory. We have some of the other authors here on the line with us, and we'll bring them in for the question and answer period. The report is entitled Integration of PV into System Operations, and I'm a research associate from the Lawrence Berkeley National Lab. I work here in the Electricity Markets and Policy Group. The purpose of this research is that to date, the research on impact of PV on utility operations has been somewhat limited due to insufficient data to realistically model some of the sub-hourly variability of PV and issues associated with the forecastability of PV. In contrast, the body of knowledge for these particular issues for wind is much more extensive. So in this study, we wanted to evaluate the impact of PV on utility operations with a focus on these sub-hourly variability issues and uncertainty from the day ahead down to hour ahead to real time. And we wanted to better understand which issues might be different from managing the same sort of variability and uncertainty from load and wind. We also wanted to understand some of the changes to utility operations in order to manage high penetrations of PV and to also identify some of the costs associated with managing the sub-hourly variability and forecast errors. To do this, we developed a case study of the Arizona Public Service System in Arizona and applied a simulation framework to this particular case. Early in this project, members of our team met with staff from Arizona Public Service. Ron Flood of APS was kind enough to organize meetings between our team and 3 key functional areas within APS. This is resource planning, generation scheduling, and transmission system operations. And based on what we learned through these discussions, we developed a modeling framework that tries to capture some of the key elements in this decision-making process that utilities use in their operations. We then apply that framework to a case study of APS with and without PV. And we evaluate the impact of PV by examining 3 key metrics. We focus on integration costs. We also focus on reliability, as measured by a Newark balancing standard called the CPS2, and we measure the score of that as sort of an indicator of the performance of the utility in managing balancing. And we also look at curtailment of renewables. Our definition of integration costs, one of those metrics, is based largely on the way that integration costs are used by resource planners at APS. And so I'll just kind of walk through a little bit of how APS uses integration costs to explain our reasoning here. So at APS, the resource planners use a production cost model to evaluate the operating cost of different portfolios that they're evaluating in their integrated resource planning. This production cost model accounts for hourly variability of wind and solar in dispatching different generation. But this production cost model doesn't directly account for the imperfect forecastability and sub-hourly variability of PV. So what the production cost model generates when it estimates the total cost is this red bar off on the left. So that's assuming essentially that there's perfect forecastability of PV and no need for increases in balancing reserves. They know that the true cost of portfolios will be somewhat higher once you account for the sub-hourly variability and forecast errors, and you bring those estimates into portfolio costs. So these increasing costs is shown by the green and purple bars. To do this, resource planners add an integration cost to the production cost model results to adjust for these missing elements. These integration costs are estimated through more detailed offline analysis that's done outside of this normal IRP planning process. So this leads us to our definition of integration cost. For us, it's this difference in the cost of a portfolio when you've fully accounted for all of the sub-hourly variability and forecast error costs, which is that purple bar, versus the cost of a portfolio where you've only accounted for hourly variability, but you haven't accounted for forecast errors or sub-hourly variability. There's many different definitions that you could use for integration costs. So this is the one that we chose to use. And so unfortunately, the same term might be used in different ways in other studies. So that's just one caveat when interpreting these results. And so one of the requirements of this project was to develop a way to calculate both this purple bar that has all of the costs associated with forecast errors and balancing reserves included, and then compare that to this red bar, which is a case where we've ignored those issues, and estimate what that difference is, and that's what we call our integration cost. So here's a kind of a flow chart that shows the simulation framework that we used to model some of the decisions that are made in utility operations. So the first thing it's done is that some of the units that APS uses to balance their system are slower starting units. And so those have to be committed during a day-ahead process, somewhat based on inaccurate forecasts made prior to the actual operating day. Since these commitment decisions are made based on inaccurate forecasts, the commitment is not necessarily optimal, which means you might end up with sort of too much generation or too little generation had you known what the true renewable or load output might have been. So in the hour ahead, you're able to adjust some of the commitment decisions for these quick starting units, things like combustion turbines. You're also able to adjust schedules of online generation. Now, in the hour ahead, you have a much better realization of what the actual output might be from renewable generators or also from the load. So you're able to sort of reduce the forecast error and make better decisions now, but you have a limited number of options available now in the hour ahead. So then also in the hour ahead, we have modeled the utility as holding some resources in reserve during the hour ahead scheduling process in order to balance the system within the operating hour. And this is in addition to any contingency reserves that they would otherwise need to hold. So this question of how much additional balancing reserves should the utility hold during the hour ahead scheduling was also one of the questions that we had. And so I'll walk through that process of how we set these reserve rules. And in particular, what we're trying to do is capture 95% of the deviations from the hour ahead schedule. So I'll walk through that here in a moment. So what we learned was that hour ahead schedules are set largely at least 30 minutes prior to the operating hour. This schedule is based on a forecast of where they expect generation and load to be during the operating hour. So we have here shown the different forecasts you might have that you would generate 30 minutes before the operating hour, and those forecasts aren't necessarily going to be accurate all the time. But that's what we're going to use to generate schedules. So these blue lines now show the schedule that might be generated, and that schedule will include a 20-minute ramp between each hour, but then during the rest of the hour, that schedule is flat. And then we can measure how much the actual wind and solar and load, for instance, deviate from those schedules by using 1 minute actual output from these different sources. So then we calculate these deviations from hour ahead schedules based on a full year of data. And then based on that, we're able to then set a balancing reserve rule that's held in the hour ahead scheduling process by essentially trying to capture 95% of these deviations that we saw. Now we did that using 1 year of data, but then we go ahead and apply that same sort of balancing reserve rule to a separate year of data. So I'll illustrate that here. So now, in this case, we're able to apply these balancing reserves to a new set of data to actually evaluate how well would those balancing reserve rules do if we were to have those resources available to balance the system in real time. So this chart here is showing the deployment of balancing reserves. And in some cases, you're not able to capture all of the deviations from the hour ahead schedule through the deployment of balancing reserves. So this difference between your deviations and what you're able to deploy ends up with what's called the area control error, or the ACE. And so when you have ACE, that means that you're not able to necessarily keep up with the deviations that you're experiencing through the deployment of balancing reserves. The NERC balancing standard that measures performance, one of the NERC balancing standards, it essentially says that it's okay to have some variability in ACE, that you're allowed to have some of that as long as it maintains within a threshold that's set by NERC, and it's called this L sub 10 threshold or parameter. And as long as it's smaller than that, then it's okay. You don't have to chase all of those small deviations. So I've sort of illustrated here a line that represents that threshold. When you exceed that threshold for more than 10 minutes, though, now you sort of have violated that CPS2 constraint, and the NERC balancing standard says that you can only have your 10-minute average of your area control error exceed that level 10% of the time. So 90% of the time you have to be within this threshold level. And the amount of time that you're outside of that threshold is what goes into calculating your CPS2 score. So we're going to use this sort of simulation to create the balancing reserve rules and then to evaluate how well you're able to maintain this CPS2 score and with the data sets that we developed. So next here we have, I'll show you our case study that we applied to Arizona Public Service. And we looked at the year of 2027, which was the last year in APS's 2012 Integrated Resource Plan. So the generation mix that we picked was based on the generation mix identified in this 2012 IRP. And the low PV scenario that we have here, we have these two different scenarios of low PV and high PV. In the low PV scenario, the amount of PV matches what was included in their base case plan. And then in a high PV scenario, we match their expanded renewables case and essentially assume that all new renewables that are added in the expanded renewables case are going to come from PV. And in the low PV case, we've got a mix of distributed and utility scale PV. And then in this high PV scenario, the additional PV that we're adding is all coming from additional utility scale PV plants that are added in southwestern Arizona. And these are approximately 200 megawatt plants that we're modeling. And so in order to model these scenarios, we developed 1-minute data sets of wind, PV, and load. And the 1-minute data sets are based off of hourly satellite-derived data, which we then add 1-minute variability to based on methods that are described in the appendices of the report. The key to understanding that methodology is that we try to account for correlation between the different sites and also sort of the expected variability that you would have within each individual site based on the cloudiness level experienced during that hour. We also have day-ahead forecast errors for the load that were provided from APS, and then we have day-ahead forecast errors from wind and PV. These wind and PV day-ahead forecast errors were based on the Western Wind and Solar Integration Study data set. And you can see some of the metrics here that show the metrics of the forecast accuracy for load, wind, and PV in these different cases below. So now I'll start to kind of present some of the results from this case study. So we went through that process of estimating what the balancing reserve rules would be required for hour ahead. And we applied that methodology to a case that was just done for load and wind, but didn't include any PV. So that's what's shown in this black line here. And then we also did that for a case that has load, wind, and PV, and we calculate those balancing reserve rules again in the red line. So on the left-hand side, in the low PV case, we see that there is an increase in balancing reserves that's required based on these 1-minute deviations from the schedules. But the increase is fairly modest. So we have just a small increase from the black line to the red line when we add PV. In the high PV case, though, we start to see a more pronounced increase in the need for balancing reserves. And we have balancing reserves both in the up direction on top and then in the down direction on the bottom. But this increase is not necessarily needed all of the time. It's just part of the year that we see the increase, and that's basically during the times when the sun is out. But one of the bigger challenges we saw wasn't necessarily just this increase in need for balancing reserves, but it was also issues associated with low net load periods with high PV and low load, particularly in the spring. And since we only modeled the APS system, we didn't include the broader WEC system. We essentially had to have all the APS generation decreasing its output whenever the PV that we're modeling is producing power. So these red lines on the left here show the hourly load over the year, less the wind and PV generation, and also less the balancing reserves in the downward direction. And then these horizontal lines on the kind of in the lower part of each of those charts shows the minimum generation level of must-run units and the output of the Palo Verde nuclear plant. The dark line is based on the Palo Verde plant being online at full output at all times. And as you can see, the red line sometimes falls below this minimum generation line, indicating potentially a need to curtail renewables. And with high PV, we see that if you have this constant nuclear output, then you end up with a fairly high curtailment of renewables that's needed. We felt that this constant nuclear was not necessarily a reasonable way to model the system, given that APS does have options to trade power with other utilities, or it has other options available to increase the flexibility of its generation fleet. So we run the simulations first with this constant nuclear assumption, but due to this high curtailment, we assume that some steps will be taken to increase the flexibility in the downward direction in the future. So we chose in our modeling to use a flexible nuclear option to represent these changes that will be needed. And so we allow, in this flexible nuclear case, the output of the nuclear plant to ramp down to 50% of its output. So it's not going all the way down, but just down to 50%. And by doing that, we're able to relax a lot of these constraints that we saw around that were leading to a lot of curtailment, particularly in the springtime period. I'll just illustrate that a little bit more in detail with some hourly plots for particular seasons. So these charts show the actual dispatch of the APS, our modeled dispatch of the APS system with low PV on the top part of it and high PV on the bottom for a week in the spring, and those are on the left, and then also a week in the summer on the right. So during the summer, it's primarily gas generation that's displaced by solar. Combined cycle gas turbines and combustion turbines provide the majority of the flexibility that's needed to manage solar. In the spring, the load is low and the solar generation is high, leading to solar to displace coal generation. In the middle of the day, we also found that the nuclear plants would be dispatched down in this high PV with flexible nuclear case. So that wasn't needed much in the summer, but in the spring we did see that start to happen. And so the main point here is just to reiterate that if you don't have alternative buyers of power in these spring months, then flexibility in the downward direction is going to be particularly challenging to manage. So let me walk through a little bit about how we take this modeling that we did now and start to calculate the integration costs and parse that out between the costs associated with balancing reserves and with day-ahead forecast errors. So these columns on the left here show the total cost of operating the different portfolios with low PV or high PV. And in the first column, we have the total cost, assuming that we can perfectly forecast the PV and that we don't have any need for additional balancing reserves. So that was our bar that was on the far left. And then we can just incrementally add the need to have balancing reserves and see what the costs now are of meeting that same situation, but just adding in the balancing reserves. And so we see an increase in costs that we can quantify, and then we can go even further and start to add in the forecast errors based on the day-ahead commitment of some of those units. And so we see that final increase in costs, and now we can look at the difference between those portfolio costs to come up with what those integration costs are. So we divide those differences in costs by the amount of PV that was generated, and we come up with an integration cost in terms of dollars per megawatt hour of PV. And so in the low PV case, the resulting integration costs, shown on the far right, was on the order of about $2 a megawatt hour of PV. And then depending on our assumptions about flexibility in the downward direction, whether or not we had this constant nuclear or flexible nuclear case, we saw integration costs in the high PV case somewhere in the range of $2 to $4 a megawatt hour. The integration costs were lower in the flexible nuclear case, but then we saw it was much higher if nuclear had a constant output. And we also see, I'll show later, that we had curtailment of renewables needed to increase. And so by adding this intermediate step, we're able to sort of parse out how much of this total integration cost is due to balancing reserves versus forecast errors. And we saw that on average, it's the balancing reserves that end up being somewhat more expensive than the forecast errors. That's on average. So let's unpack that a little bit more. In the next slide, we show each day we sort of estimate essentially an integration cost for every day, and we again parse this out between balancing reserves and forecast errors. And one of the things that we saw is that although balancing reserves were on average kind of a little bit more expensive, the forecast errors, there were particular days that were more challenging. So there were more expensive days sometimes with dealing with forecast errors. And so that's what the sort of red tail here shows, is that there are some particularly challenging days, but those didn't occur very often. So on average, the cost of forecast errors ended up being lower than the balancing reserves. But on particular days, you might have some volatility that will be challenging to manage. We can also look at how did the utility deal with some of those day-ahead forecast errors. And one of the ways that forecast errors on the day-ahead were dealt with was through some sort of redispatch of generation within the operating day. And what this chart here shows is the different sources of redispatch, essentially. So in our high PV case with flexible nuclear, we can look at how much the megawatt hours of gas turbines, for example, changed between the day-ahead schedule and then what they actually needed in real time. And that difference illustrates how much we were sort of adjusting their output in response to more information from the better forecasts or the actual that arrived that day. And so a lot of the flexibility is coming from combustion turbines and combined cycle plants. We see a fair amount of it also coming from coal, and then a small amount coming from the nuclear in this case. And one of the things that APS was interested in is trying to understand how much they might need to think about having available to essentially pull from, if they're nominating their natural gas on the day ahead, and they need to be able to either use more natural gas during the operating day than they expected, or they don't use as much as they had expected, what might they do with that natural gas? And currently, one of the options is that you can essentially store that natural gas during the day. And so we sort of modeled very, very simply the use of natural gas storage as something that could provide more gas during the day or absorb excess gas if you didn't need to use all of it. So this chart on the bottom just sort of shows essentially our daily gas consumption compared to how much we might need to withdraw or inject into storage. We don't necessarily see a great increase with the amount of storage that's needed for natural gas with the high PV case. But one thing we do see is that the average natural gas consumption decreases, yet our storage use still is fairly high. So the amount of storage needed compared to the average consumption is going to increase. We can also go now and start to look into the performance during the operating hour. So now after we've got our hour ahead schedule set and we measure how well the utility is able to balance the system, we can calculate this area control error in these different cases. And so that's what's shown on the top chart here is the area control error over the whole year. And the blue bar in the background shows that L sub 10 parameter. So it essentially shows the threshold by which if your ACE is within that level, then it doesn't really matter too much. But if the ACE exceeds that level for more than 10 minutes on average, then you start to end up with CPS2 violations. And so essentially in our low PV case, or with just load and wind, we were able to achieve a CPS2 score of 96% is what we were able to do with the way that we modeled balancing reserves. When we add PV to this case, we're able to still maintain that same level with the balancing reserves that we added. So we're able to maintain right around 96%. But then in the high PV case, we started to see that there were a few more events that we weren't able to quite keep up with. So setting balancing reserve rules in the same manner, even though we increased the amount that we had, we ended up with a slightly lower performance. So we still exceeded the minimum threshold of 90%, but we were starting to see a little bit of a decline. And so that's something that might need to be addressed is thinking about alternatives. So we go into a few more options there in looking at that. So here we have some of those options. So what we looked at what I just presented in that previous table was the high PV case with flexible nuclear, what our integration cost was, and then what our balancing performance was as measured by that CPS2 score. And so we had a slightly lower performance than we'd want, that we saw with the load and wind case, still exceeding that minimum 90% threshold though. So if we looked at other options, such as increasing our balancing reserve rules even more, or another option would be to increase the rate of deployment of balancing reserves. So if we made it so that balancing reserves could be fully deployed in 5 minutes versus 10 minutes, then we saw that we could increase our CPS2 score. Or if we really increase our balancing reserve, we could really crank that CPS2 score up. But by doing these things, we did see an increase in cost. So there's sort of this trade-off that you can increase your balancing performance, but you start to increase that integration cost to some degree. And so there's sort of a trade-off here that we saw that's important for people to keep in mind. Finally, just a few more results. We did some sensitivity analysis to try to just better understand what factors might impact the integration costs that we saw. So we did some various sensitivity cases around these balancing reserves or the amount of flexibility available or fuel prices and so on. And again, we saw largely a consistent result, which was that the balancing reserve costs were more expensive than our forecast errors, but that we didn't see dramatic changes in these costs. That things like adding more balancing reserves were things that would try to drive up our costs more, but things about choosing the right gas price and so on didn't have as much of an effect. We also looked at renewable curtailment. So again, if we had this flexible nuclear case, we had adequate balancing down in that case, then we ended up with only a fairly modest renewable curtailment of about 3%. But if we started to increase our balancing reserves, we might end up in more curtailment. We did a case where we tried to minimize the curtailment by introducing penalties into the model for curtailment, and we could drive it down even further. And again, some of the gas prices didn't necessarily affect that too much. So, okay, and then so this finally is a summary slide that is in our executive summary that shows the total results. I think just a few takeaways from here. If we work from the left to the right, what we saw in our low PV case was that we had a modest increase in the amount of balancing reserves that were required, but that the utility was able to largely maintain its same balancing performance as what we saw in the no PV case. That modest increase in balancing reserves and the issues around day-ahead forecast errors, we calculated a cost associated with that. It was on the order of $2 a megawatt hour, and we saw a small amount of curtailment of about 3% or so over the year. When we start to add the high PV case and we get to higher PV penetrations, we did see a larger increase in the balancing reserves that were required, and some of those deviations were significant and somewhat more fast, and so that ended up having a slight decrease in our CPS2 score. And that with the constant nuclear case, we ended up with a larger cost associated with the balancing reserve. So now we bumped up our integration costs more towards the $4 a megawatt hour range. The biggest issue, though, was curtailment of renewables. We just ended up with too much curtailment, it seems like here. This is almost 18% of our renewables being curtailed. So what we saw was that we need some source of flexibility in the downward direction. That can come from different sources, but one of them that we were able to model in this case was by allowing the Palo Verde nuclear plant to be more flexible and to go down to 50% of its output. And by doing that, we were able to relax this renewable curtailment and bring that back down to a level similar to what we saw with low PV. And then we were able to also see that the integration costs were reduced. So that comes to our final sort of recommendations and areas for future work. And I think that for us, to some degree, we ended up having to focus somewhat on, in the high PV case, on identifying these flexibility resources in the downward direction. And so some of this might come from identifying potential buyers of power for surplus power, especially in the spring. Also looking at potentially being able to provide balancing reserves from renewables. That's not something we did in here. But if you're otherwise going to curtail renewables, then in some cases you can provide balancing from those resources. And then there's also a lot of other options in terms of things about load shifting or energy storage. And then if we focus just on those sub-hourly variability issues, there's a lot of things also that are being talked about that we didn't model in this case that are important to sort of understand as options. So one of them is that energy imbalance markets that have been talked about in the West and are sort of moving forward with PacifiCorp and CalISO and potentially NV Energy also, those can increase access to resources for balancing. And so something like an energy imbalance market is something that can help relax some of these constraints that we saw. And then also NERC has proposed a new balancing standard that's moving through the process. And essentially one of the things that does is that it starts to be less stringent than a CPS2 balancing standard as long as the overall system is maintaining well balanced. So it sort of matters more what the overall interconnection is doing. And so it's a little bit more challenging to model. You can't just look at an individual utility on its own. But I think that's an area that might be interesting to look into further, is to understand how this new balancing standard would compare to this old one of the CPS2. Also looking at alternative providers of reserves like demand response. One of the things that's of interest is to think about how can you better account for this uncertainty in making your day-ahead commitment. So can you do things like stochastic unit commitment or other commitment methods that can sort of help you make better decisions in the face of forecast errors. So those are other things that we didn't consider but might also help increase the ability to manage variable renewables. So we just wanted to say thanks real fast to APS. They were very helpful in providing some guidance to us and data and providing these meetings with us. Also to the Department of Energy and the Sunshot Initiative for sponsoring this project. And we're responsible for any errors in this analysis. But you can download the full report at this link here. And at this time, I think it makes sense to start moving into some of the questions. So thanks for that. I see a number of questions in here. Auden, I don't know if you see these questions also?
No, I don't.
Okay. So I have these on my end. So let me start with some of these, and I'll pose those first to you, Auden. Maybe you can talk about some of them. So one of the questions, just for clarification, is: do the sensitivities also assume flexible nuclear?
Yes, I can take that one. So this is Auden Botcher at Argonne National Lab. So the sensitivities that Andrew showed, that they assume flexible nuclear operations. There are a few others shown included in the report, but the ones Andrew just talked about, that they assume flexible nuclear. Yes.
Okay. And then another question is does the commitment logic require reserves to be held to meet day-ahead forecast errors, or is it assumed that day-ahead forecast errors can be resolved in the hour ahead regardless of the previous unit commitment?
Yeah, that's a good question. So basically, our assumption here in this analysis was that we calculated hour ahead reserves. So they, as Andrew showed, they would increase with more solar PV in the system. We imposed the same level of reserves in the day-ahead unit commitment. So we didn't explicitly account for the day-ahead forecasting error in the day-ahead unit commitment schedule. But when we do the recommitment at the hour ahead or rescheduling at the hour ahead stage, the model would make use of any available resources to accommodate that uncertainty.
Yeah, so I think that's an important point, that essentially we don't necessarily position the system in the day ahead to be able to handle forecast errors. We don't explicitly include any constraints in the day ahead commitment that would sort of, save something in reserve. But then we simulate what happens when you have the actual forecast errors show up in the hour ahead, and we have these essentially recourse actions that the utility can then use, and that's doing things like starting fast start units or changing the dispatch of units that are already online. And what we saw was that we were largely able to meet all of those requirements in the cases that we focus on, even though we weren't doing anything in the day ahead to sort of prepare for those day ahead forecast errors. So we saw there was enough flexibility in the system to manage that. That did come at the cost, though, and so that's where some of those day ahead forecast error costs come from, is that you essentially had to rely on something that was maybe a little bit more expensive in order to manage that. That had you had a better forecast, you wouldn't have to call on that resource. So, that's one way that we chose to model this, and that's where things like stochastic unit commitment and other methods might start to look into more about how can you position a system given that uncertainty that you have. So one question is, for Palo Verde, are there any current contractual or operating constraints that prevent it from operating that I guess require it to operate in the way that it is currently?
Well, I can take a first shot. So yes. Let's be clear about this. So when we did this assumption in analysis, that was not based on a recommendation from APS. That was our own assumption. So APS did not really agree, or that they would see other sources of flexibility being more likely. So I don't know about the exact operational or regulatory aspects for the plant. But I could add that I know that in Europe, in Germany and in France, there is experience with operating nuclear power plants in load following mode. So at least for certain types of plants, it is technically feasible. But again, it may not be the best or the option that you want to pursue first.
Yeah, and I just want to add that in reviewing this result, APS was fairly uncomfortable with us choosing that option, and we sort of had limited levers available to us to model more flexibility in the downward direction, and so this was sort of a modeling assumption that we needed to make. But they felt that currently they don't operate Palo Verde in that way, and they don't necessarily see that happening in the near future. So I think Auden's point about experience in other regions is helpful, but it is something that would require a lot more thinking, and other options might be easier to do than making nuclear plants more flexible. So one question was, how comfortable would APS be with operating their system at a CPS2 performance of 92.6? So that was the CPS2 score that we ended up with in the high PV case in our first one, and that was another one that APS raised as a potential concern. They actually informed us that they aim to have a much higher CPS2 performance, that's important to them to maintain balancing. And so when they saw 92.6, they were again fairly uncomfortable with that they thought that was low. And so our sensitivities, where we started to look at what are some options to increase that standard, were in response largely to APS's concern about that lower level. So they would like to see that higher. I think the important thing to note is just that the 90% CPS2 score as sort of a minimum floor that's required for compliance, and that you just don't want to go below that level. So the key is to be somewhere above that, and I think APS wants to ensure an adequate buffer above that.
And if I can add to that, so as one of the charts that Andrew showed illustrates the trade-off there, that you can always increase your CPS2 score by allocating or using higher amounts of reserves, but that comes at a cost. So it would have to be up to the individual utility to decide where on that trade-off curve they are most comfortable. And things may change if we move towards a different balancing standard, as Andrew mentioned towards the end there as well.
There's a question about how does our method in setting these hour-ahead balancing reserve levels compare with current practice in APS and elsewhere? And largely what we learned from APS is that they have a contingency reserve requirement that they have to hold. So they have sort of rules for that. But then they also essentially, it sounded like they will have sort of rules of thumb that they use in order to ensure that they're going to be able to manage what happens within the hour. So they sort of have more of a rule of thumb approach based on their past operating experience that informs them about what they might need to hold back during their hour-ahead scheduling in order to maintain the system without having to dip into those contingency reserves. And so they sort of informed us a bit about that process. What we did in order to model that was to create this sort of balancing reserve rule that was 95%. And so that came out with a number that I think is largely around, with just focusing on the load variability and forecast errors. That's sort of in the range that seemed like it was comparable to what they talked about. So the method is different, but the sort of outcome was similar with just focusing on load and the small amount of wind that they have now. Now, as you start to go to higher renewable penetration, that's where it becomes maybe more important to think about developing that new rule of thumb, and essentially that's what we tried to do with these new rules. The approach that we applied here is quite similar to approaches that have been talked about elsewhere. So there's a fair amount of work out of the Pacific Northwest National Lab with Yuri Makarov and others that sort of does a more detailed version of what we did. We sort of did something similar to that. We have kind of a table at the end of our appendix that sort of walks through other approaches that have been used for calculating these balancing reserve rules and try to do some compare and contrast. But largely the idea behind it is similar, if not the specifics of the method. So one question was, how would the use of batteries in conjunction with PV affect this analysis? Auden, do you want to take a crack at that?
Yes, sure. I can take a first crack. So we did not model energy storage at all in this study. Would be an interesting thing to do in future follow-up studies. But basically that should help out in balancing the system and contribute towards this, solving these oversupply situations that we sometimes would see, particularly in periods with low loads. So if you could, store some of the PV during hours of surplus in the system, that would reduce your curtailment of renewables, and I would also predict that it would contribute to lower the overall costs of the system. So I guess the question is whether the cost of energy storage itself, how that compares to the benefits to the system.
Yeah.
So that would be an interesting analysis.
I think one follow-on with that is just that the degree to which batteries can help mitigate these issues somewhat depends on the amount of energy that you can store in those batteries. So if it's a sort of a short-term battery that can store energy for, say, 15 minutes or even as much as an hour, that might help with issues around the balancing reserves and the shorter-term variability, that you can smooth some of that out and reduce how much you'd meet with balancing reserves. But if it's only a small amount of storage like that, then it might be harder to deal with issues around overgeneration. If you can't shift that PV generation into later hours, for example, then you might not be able to deal with that. So you might need to start talking about, say, 2 or 3 or 4 hours of storage. I think that's another kind of leads into another question here that was just sort of more broadly, why didn't we look at these other issues around demand response and energy imbalance market, pumped hydro, or any other resources to address balancing? And then sort of a follow-on to that is, do we include the Solana CSP plant, which does have 6 hours of thermal storage? So the Solana plant we didn't include in this analysis. So we're doing everything with wind and PV in this particular case. And because the Solana plant does have that 6 hours of storage, some of these issues, both with overgeneration and with the shorter-term variability, would be reduced. So we were largely focused just on PV and kind of wanted to understand this from the perspective of PV. So that's why we didn't focus on the Solana issue. And then I think the question about demand response, energy imbalance markets, and other options, I think those are all very valid. And essentially what we were looking at is sort of taking the tools that are most used right now and just applying PV to that and seeing what the result would be. And I think that helps to motivate the need to look into these other options. So we start to see what are the issues that maybe could be addressed by introducing demand response or providing an energy imbalance market or pumped hydro. So we didn't include those things, but I think that's a very logical extension of where this would go for our own analysis, but also then just for utilities to consider as issues that or options that might be available to them to help manage some of the issues that we saw arise here without those options. We've got time for a few more questions. Oh. Maybe Auden, you can answer this one. Is what is the range of % of delivered energy coming from renewables in the various scenarios?
Let's see. So let me make sure I understand the question. So the range of % of delivered renewable energy. So I guess that you can see by looking at the curtailment numbers, I suppose, right, Andrew? So
maybe let's just talk about broadly what were the amounts of renewable energy total just in the scenarios that were available before getting into the curtailment part of that. Do you recall those numbers off your head?
It's in one of your slides.
Yeah, I'll back up. I think the case study slide maybe has that in more detail.
Yes. So it's for wind power. It was 5%. Yeah, there we go. 5% of the total load. So the available wind power energy, assuming no curtailment, was equal to 5% of the total load in the system. And for PV, under low PV, with equivalent definition, 9% PV under the low PV assumption and 17% available PV resources under the high PV assumption. And then, so that's what we feed into the model. And then when we look at the results, we have to then subtract from those numbers the level of renewable curtailment. And in the low PV case, that was very low, close to negligible as far as I recall. In the high PV, it depended a lot on our flexibility assumption, as Andrew pointed out. If we do assume the fixed nuclear assumption and none of the other flexibility options, like trading or demand response, energy storage, and so on, we got as much as 17% curtailment. So I guess that would bring that PV penetration down to, I would guess, maybe 14% or something like that instead of 17%. Whereas with the added flexibility that we we chose to consider nuclear, flexible nuclear, the curtailment dropped down to around 3%. So in that case, the actual use of PV and wind is close to what you see in that table there.
Mm-hmm. I think a related question to that is, would the grid be harder to manage if the capacity was more residential PV? So in the low PV case, we have a large share of the amount of PV is coming from distributed PV, and then the remainder is coming from utility scale plants. In the high PV case, we have the same amount of distributed PV, but now we've increased the amount of utility scale renewables that are available. And so I think there's a fair amount of questions just about integrating distributed PV into the distribution system that we don't go into in this study at all, because we're essentially looking at sort of a broad footprint of the overall utility footprint. So I think there's one issue is just what are the impacts of the distribution system, and there's a fair number of studies that look at issues around on that and options that we don't consider. The other question is how much visibility might the utility have over variations and forecastability and things like that. So that's one issue that people are working on is trying to be able to get more visibility to distributed PV resources. So there's options available for generating forecasts, and that's something that APS is actively working on, is trying to just get better estimates of what portion of PV is showing up at different times from distribution resources when they don't have a direct meter that they're measuring, on a short-term basis like they do for the utility scale plants. So I think aside from just those visibility issues, there actually is a benefit to distributed PV in that it has sort of a broader footprint, so it's sort of more spread out than some of these utility scale plants. So the amount of variability that we saw from our distributed resources on aggregate was somewhat smaller than what would come from these large 200 megawatt PV plants that we were modeling. So there's sort of two sides to it, I guess. There's sort of the impacts of the distribution system versus sort of the potentially smaller amount of variability because you have a larger footprint and it's more spread out. On balance, I can't necessarily say which one would be easier or harder, but there are trade-offs.
So maybe if I can add to that. So in the study we did differentiate between distributed and centralized PV and in terms of the ability to curtail those resources. So we assume that the system operator does not have the ability to curtail distributed PV, but can curtail centralized PV if needed. So from that perspective, distributed is more difficult to handle because you don't have any control over it, as Andrew said. So whereas for assuming you can control centralized PV, you have that added flexibility of potentially backing down that generation during periods when that may be needed.
So here's another question that's a good one, which is, can we provide an example of how an energy imbalance market might provide access to balancing reserves? And so maybe if I just kind of step back a little bit. So we essentially were assuming that the utility would have to create these fairly flat hourly schedules, and that within the hour they would have to rely on their resources to be able to balance whatever happens that's going to be different from that hour ahead schedule. And so the resources that we set aside in order to do that is what we called the balancing reserves, and all of those resources were from APS generation that was available to do that. And so with an energy imbalance market, essentially what that allows is that if you have some deviation from your hour ahead schedule, you no longer only have to rely on your own resources in order to help meet that deviation, that now you can have potentially other resources that are in a different neighboring utility or somewhere else, that if it's easier to meet that imbalance through resources on their end, or if, for instance, they actually have an imbalance that's going the opposite direction, you can potentially maybe net these things out or use the cheaper resource to be able to do that. So what it allows is essentially you can have additional resources that are available to help meet that within our variability, and you have to hold. You wouldn't necessarily need to rely on as much resources being held within your own footprint in order to manage that. So that's sort of essentially where an energy imbalance market might start to provide some benefit. So again, we don't go into actually trying to model that. I think there's a lot of great work that's been done on sort of looking at energy imbalance markets from E3 and then from NREL and Pacific Northwest National Lab. Some of the energy imbalance market work that's come out of like WEEB and other organizations can kind of help explain a little bit more about what some of those options are. So I'll point you to those resources for more.
Yes, and just adding from a modeling perspective, in a study like this one, or one individual utility, it is challenging to represent an energy imbalance market or any trading with neighboring regions without actually modeling ideally the full Western interconnection, I suppose, and that was beyond what we could do in this study.
Okay, and then just a last question here. There's a question of what was the motivation for this study, and we should note that I don't know if I mentioned it in the presentation, but there's also a study that Black and Veatch did for APS that was finished before this study was. It's maybe about a year or two old, that also looked specifically at integration costs. And so APS actually hired Black and Veatch to do this study for APS to help them provide that number that they use in their analysis. So our interest in this study was to look a little bit more broadly at some of these issues and sort of try to dig down deep into what's going on in the utility. I think we have a couple additional wrinkles to what we did, which is to also include things about day-ahead forecast errors. So that part of it is sort of thinking about how do you deal with the forecastability of resources was something in addition here. So we sort of complemented that study, I think, to some degree by adding some different levels of analysis. The other thing is just we did push harder on adding a higher PV case than I think what was done in the Black and Veatch study. But that's available on the web also, and you can email me. I can try to help point you towards that study if you want to look at that in more detail.
Yeah, so just to emphasize that the purpose was really not to look at APS in particular here. We chose that as, for our case study because of its location and its interest in PV. But the original purpose was to look to apply a comprehensive analytical framework and look at these issues of PV integration for an individual utility.
Okay, we're at the top of the hour, and so thank you all for your questions and for attending this. This has been a great set of questions. Do feel free to email any of the authors if you want to follow up with anything directly. I'll put that slide up again that has our email addresses. We will post this webinar to our website since we have a recording of it. So visit the emp.lbl.gov if you want to point anybody towards this webinar. And really, again, thanks so much, and we look forward to talking with you about this more. Thanks.